Hello everyone and welcome to the OneClass channel. My name is Jeff Krause. I have a PhD in chemistry and today I'm going to run through a set of undergraduate to upper high school level chemistry questions. More specifically, I'm going to be running through acid-base questions today. So here's our first question. So it's two parts. So give the conjugate base of NH4 plus. So our acid-base reaction with NH4 plus is going to be with water, and we're going to get so we're going to transfer a hydrogen to get NH3 plus H3O plus. And I'm just going to migrate this to make sure it's visible. And okay, so when we're identifying conjugate acids and bases, okay, the species that lost the hydrogen and the species that gained the hydrogen are both pairs, right? So NH4 plus and NH3 are acid-base pairs, and H3O plus and H2O are acid-base pairs. So to answer the question, the conjugate base of NH4 plus is just NH3. So NH3 is the conjugate base. Okay. Give the conjugate acid of HPO4 2 minus. Okay. So for conjugate acid, then we're talking about a base reaction here. So we've got HPO4 2 minus. And so now it's accepting a hydrogen, H2PO4 minus plus OH minus. And so again, these guys will be acid-base pairs, and these will be acid-base pairs. Okay, so then we've got H2PO4 minus and HPO4 2 minus are acid-base pairs, and H2O OH minus are acid-base pairs. Okay, and so we're looking for the conjugate acid of HPO4 2 minus, so that would be H2PO4 minus. So then H2PO4 minus is our conjugate acid. Okay. So checking through the solution that's posted, a pair of acid and bases that differ only is called a conjugate acid-base pair. So the conjugate base of NH4 plus is NH3. So yep, that looks good. And the conjugate acid of HPO4 2 minus is H2PO4 minus. And that looks good. It's not quite the acid-base equation, but it's fine. That looks good, and that's a good way to identify acid-base pairs. Okay. Why is hydrofluoric acid a weak acid compared to other hydrogen halides? So this just brings up one important point, which is that your acid strength is inversely proportional to your bond strength. And by bond strength here, I mean the bond strength to hydrogen. So if X is, say, all the halides, then the stronger this bond is, the weaker your acid, or another way of putting it, the weaker the bond is, the stronger the acid. So if X is chlorine, bromine, iodine, then that bond is sufficiently weak and it breaks very easily when you dilute it in water, and so you get the hydrogen coming off, and you basically get complete dissociation of the acid. But then for HF, this bond is strong enough. The bond is strong enough that instead you get an equilibrium. Because now it can go back and forth, and so now you have a weak acid instead of a strong acid. And so this bond would just be strong because if you recall, right, the periodic table, or the halogens are ordered like this. So although fluorine and electronegativity would actually increase this way, although fluorine is the most electronegative, which would weaken the bond, it's also the smallest, so the hydrogen can get up very close, forming a much stronger bond, while down below, these species are so large, size being the n value for the orbitals and the number of electrons. You get much higher repulsion, as well as their electronegativity playing a part, and it weakens the bond sufficiently that for these species it breaks almost instantly, and for this it's now a weak acid instead of a strong acid. Okay, checking the solution here. So it's because the bond is strong, and it's stronger than all the other halides, which is what leads it to be a weak acid. So that looks good. Okay. So which of the following conditions indicate a basic solution? So this is just working through some pH-POH relations. So for the first one, pOH is 11.21. I'm just going to relate everything to pH because I think most people remember it that way. So recall that pH plus pOH is equal to 14. So pH is equal to 14 minus pOH, which is 14 minus 11.21, which is 2.79. And if you remember, pH less than 7 is acidic, or a pH greater than 7 is basic. So this is less than 7, so our solution would be acidic. Obviously, then we could also use the pOH scale and say that a pOH less than 7 is basic, and a pOH greater than 7 is acidic, which is what we had originally. Okay. Okay, so then for B, we have a pH of 9.42, and again, so here we have pH less than 7 is acidic, and a pH greater than 7 is basic. If we look, it's greater than 7, so that's basic. Okay, C, our concentration of OH minus is greater than our concentration of H plus. So I think most people would realize that this would mean it's basic, but just to describe why this would be. So remember that our Kw is our concentration of OH minus multiplied by our concentration of H plus. And that's equal to 1 times 10 to the minus 14. So it's a constant. So if our concentration of OH minus increases, then our concentration of H plus decreases. And remember that our pH is the negative logarithm of our H plus concentration. And also remember that in what this means, or what Kw is telling us, is that in a neutral solution, OH minus equals H plus concentration equals 1 times 10 to the minus 7. Which, if you work it out, would be a pH of 7. So if your OH minus concentration is greater than your H plus concentration, it means, because of this relation here, that your H plus concentration must be less than 10 to the minus 7. And if it's less than 10 to the minus 7, that means that your pH must be greater than 7. Right? And so that would be a basic solution. Okay. And right, and so you can't quite see the last part here, but for D, we have that the concentration of OH minus is greater than 1 times 10 to the minus 7. And so again here, we have that our OH minus H plus concentration is in balance. And so if our OH minus concentration is greater than 1 times 10 to the minus 7, then that means, because of this, that our H plus concentration is less than 1 times 10 to the minus 7. And if our H plus concentration is less than 1 times 10 to the minus 7, then our pH is greater than 7, which means that we have a basic solution. All right. So now looking back through my work through solutions and comparing with what's here. So here we have an acidic solution, so we could have used POH or pH. Here we have a basic solution as our pH is greater than 7. Here we had a basic solution again because our OH minus concentration is greater than our H plus concentration, and they're in balance. And here our OH minus concentration is greater than 10 to the minus 7, which again means that our pH is greater than 7 because they're in balance. So this looks good. Okay, so we've got hydrofluoric acid has an acid dissociation constant of 6 times 10 to the minus 4, and at equilibrium the concentration is 0.025 molar. Okay, so our equilibrium expression is going to look like this, or our balanced chemical equation is going to look like this. Our equilibrium expression then is going to be products over reactants. And we don't include water in here as it's our solvent, so it's basically everywhere. Or it's the same, it'll be the same top and bottom, and so it'll cancel. And so that's our equilibrium expression for HF. Now, depending on the values given will be how we use to solve this, but here we have our equilibrium concentration, so that means we already have this value here, so that's this, right? So there's a difference between if we're given our initial concentration or our equilibrium concentration. So that's good. And our Ka is given in the question of 6.8 times 10 to the minus 4. And now we can solve for our H3O plus concentration by recognizing that this is a 1-to-1 here. And so our H3O plus equals our F minus. And so this value must equal our H3O plus concentration squared over our HF concentration, which is 0.025 molar. I'll get rid of that actually. So the units are kind of funny with equilibrium expressions, so it's best to just drop them. Okay, and so H3O plus is equal to 6.8 times 10 to the minus 4 times 0.025, all square rooted. And if you work through this, you'll get 4.123, and then you can add in units at the end, appropriate for the quantity. And then our pH is, that would be a giant concentration, 4.123 times 10 to the minus 3. Okay, and then our pH is just the negative logarithm of this value. Again, logarithms don't like units, so we're just going to drop it there. And and so 2.385. So our pH for the solution is 2.385. Alright, so now checking through the solution given here. So there's our equilibrium expression that we had above. And then there's our pH. They do go through an explanation. So there's our balanced equation where they've, I guess, swapped A for F. But that's just a more general balanced equation. So this is for fluorine, or HF. You could make an ice table, but there's no point. Although it is showing you that at equilibrium, we're given our equilibrium value and the x's. It's showing that H3O plus and F minus must have the same concentration. So we get our value there and our pH. So that looks good. Okay. All right, so now we have a similar question, except with base, this case ammonia, so NH3 plus H2O is going to go to, we're given our base value, so that means we've got H3O plus NH4 plus, right? So we're moving a hydrogen this way. Oops, sorry. Got carried away there. NH4 plus OH minus. There we go. Moving a hydrogen that way. There we go. All right, so our Kb value is going to be equal to our NH4 plus OH minus over our NH3 concentration. Again, water doesn't get included in our equilibrium expression. It's a pure substance. Okay, so we're given that the initial concentration of ammonia, here I'll do it this way. So I'm just going to rewrite this because I put my Kb right below it. Okay, so we're given that the initial concentration is 0.390 molar, and we would have 0 of these. Our change is going to be minus x in NH3, and then plus x in each of these. And so then at equilibrium, we're going to have 0.390 minus x, x, and x. And so then we can sub these into our equilibrium expression, which we've written up above, and also with the value. So in the question, we're given 1.8 times 10 to the minus 5, and so that equals x over 0.390 minus x. So we're going to take one simplifying step here and say that because our Kb value is so small, 10 to the minus 5, it's quite likely that x is going to be small. And so this is approximately 0.390. And so what this comes out to is 1.8 times 10 to the minus 5 is equal to x squared over 0.390. So then x squared is 1.8 times 10 to the minus 5 times 0.390, which is equal to, okay, so then x is the square root of this. out that value. So that would be 2.6495 times 10 to the minus 3. Okay. And so what is the percent? What is the pH and what is the percent ionization? Okay, so we're actually in a spot to calculate our percent ionization already, as if we look, X is our OH minus concentration, and we've got our original NH3, and so our percent ionization is going to be 100% times our OH minus concentration at equilibrium over our NH3 concentration initially. So it's just how much of your initial NH3 has become ions as a rationale for it. So 100% times 2.6495 times 10 to the minus 3 over 0.390 molar, and this will also be molar. So those will cancel. And then if we do this out, it's going to be 0.679%. or about 0.68%. So there's our percent ionization. Okay, and now our pH. So X is our OH minus concentration. Okay, so our OH minus concentration is 2.6495 times 10 to the minus 3 molar. So we can solve this a couple ways. So POH is the negative logarithm of our OH minus concentration, which is the negative logarithm of this value, which is 2.577. And so our pH plus our POH equals 14. And so our pH is 14 minus 2.577, which is 11.42. 0.390, so I guess 3 significant figures. So 11.4. Again, I just kept values until the very end. Okay, so then our pH is 11.4. Yeah. Okay, so there's so there's our pH and our percent ionization. Looking through the solution as given here. As we can see here, they didn't make this simplifying assumption and use the quadratic equation. And so their value does come out to be slightly different. So 2.64 versus 2.649. So we're off in the second decimal place. If we now calculate our pH, though, it comes out to be the same. And our percent ionization also comes out to be roughly the same. Again, off in the third decimal place. But all in all, this solution is correct. In fact, the solution is probably a little more correct than what I did, but that's okay. Okay, so what is the conjugate base of H2SO4? So for H2SO4, we have, this one's a strong acid, and so we're going to get so it's hydrogen transfer, HSO4 minus plus H3O plus. And these guys are acid-base pairs as well as these. And so H2SO4, HSO4 minus is an acid-base pair. And H3O plus, H2O is an acid-base pair. And so we're looking for the conjugate base of H2SO4, so that would be this guy. So HSO4 minus is our conjugate base. Yeah. Okay, by definition, a conjugate base is the species that is formed after an acid donates its proton. So you lose a hydrogen, and you lose H plus actually, so that's why you get the additional charge. And so you drop a hydrogen and add a negative charge, so that's kind of an easy way to remember. So this looks good. Okay, 0.5 molar HCl is used with saturated calcium hydroxide, and the average volume of HCl was 19.45 centimeters cubed. We titrated with 25 centimeters cubed of calcium hydroxide. And so what we mean by titrated with is we balanced, or we reached a chemical balance here. Or in an acid-base question, it's going to be neutrality. So HCl is a strong acid, meaning we get essentially complete dissociation into H3O plus Cl minus. And calcium hydroxide is a strong base, meaning we get effectively complete dissociation into its constituents as well. So in reality, what we have in solution is H3O plus OH minus going to water. Okay, so just because, again, these are complete dissociation products, and so as we can see, these exist in a 1-to-1 ratio here. And so this is what we'll use to solve our problem here, along with these two expressions. So if we have a 0.05 molar HCl, and our volume of HCl is 19.45 centimeters cubed. Okay, so our concentration is our moles over our volume, and so our number of moles is our concentration times our volume, which in this case is 0.05 moles per liter. 0.05 moles per liter times this 19.45 centimeters cubed, and a liter Or yeah, I should have, well, I'm gonna write my unit conversions down below, just because there's a few of them. So moles per liter times this 19.45 centimeters cubed. So a liter is a decimeter cubed. So there's 1 liter per decimeter cubed. And there's, it's a decimeter per 10 centimeters. Yeah, so I should have done it the other way. Yeah, 1 decimeter, yeah, per 10 centimeters. Yeah, I should have done it this way. There's a decimeter per 10 centimeters, so that needs to be cubed. Okay, so then that'll give us decimeter cubed over centimeters cubed. These decimeters will cancel these centimeters will cancel these, and this liter will cancel this, leaving us an answer in moles. So that looks good. And when running through it yourself, don't forget the cube, right? So that's 10 cubed or 1,000. And so this works out to, where is my answer? Oh, there it is. 9.725 times 10 to the minus 4 moles. There. Okay. So the number of moles of HCl used is then this. And then from our dissociation up above here, we see that we get complete dissociation. So this is also our number of moles of H3O plus, and it would also be our number of moles of chlorine, right? So then that means that our H3O plus is our number of moles of HCl. And because these two must exist in a 1-to-1 equilibrium in this expression, that must also equal that, right? So the number of moles that we must have titrated to reach neutrality is then equal to that. So our N for our OH minus must be 9.725 times 10 to the minus 4 moles, as the two must equal each other to have reached a neutral solution. And okay, so then the third part of the question asks, so if that's the number of moles, what the concentration of OH minus in the 25 centimeter cube solution of calcium hydroxide was. So the concentration of OH minus is then our moles over our volume, which in this case is 9.725 times 10 to the minus 4 moles over our 25 centimeters cubed. And again, we're going to need to multiply by 10 centimeters per decimeter cubed, and a decimeter cubed is a liter. So that'll cancel these decimeters, this will cancel the centimeters, and we're going to end up with moles per liter, which is what we want. And so if we work this through, we'll get 3.8 9 times 10 to the minus 2 moles per liter. Okay, and so that's our concentration of OH minus. And then it asks us now to calculate KSP for calcium hydroxide. So I'm just going to rewrite the calcium hydroxide dissociation down here, just so that we have it. Okay, so our KSP, also that's solid, and these are aqueous. So our KSP is just going to be our concentration of calcium 2 plus times our concentration of OH minus squared because of the 2. We have our concentration of OH minus, but from our balanced equation, we can see that our concentration of calcium 2 plus must be, so our concentration of OH minus will be double that of calcium 2 plus, or our calcium 2 plus will be half that of OH minus. So it should be our concentration of OH minus over 2, which is 3.89 times 10 to the minus 2 over 2, that's molar, or 1.945 times 10 to the minus 2 molar. Okay, and so our KSP is just 1.945 times 10 to the minus 2 times 3.89 times 10 to the minus 2 squared. And if we work this through, it is 2.94 times 10 to the minus 5. And then, so there's our KSP. And so I believe, that's all 3 parts of this question. So you can also write a balanced chemical equation for the whole thing, but HCl and calcium hydroxide do completely dissociate, but you can write it like this. If you do it this way though, as they've found, you calculate your number of moles of HCl, and then you would need to divide by 2 to get your number of moles of calcium hydroxide, but then you would need to multiply by 2 to get your number of moles of OH minus. And so then your number of moles of OH minus still comes out to be 9.725, because your number of moles of OH has to equal your number of moles of H3O plus. Okay, so that looks good. So then for getting the concentration, you divide by your volume, so you get this 0.0389 or 3.89 times 10 to the minus 2, so that looks good. And then for the KSP value, you need your concentration of calcium 2 plus, which is just half, so about 1.0195. So I've got an extra decimal place there, but that's okay. And it turns out that extra decimal place changes that second decimal place value, but again, it's close enough. It's just off by rounding error, so our KSPs are the same. So that all looks good. Okay, what is the conjugate base of HCO3 minus? So if we're looking for a conjugate base, then we're going to do our acid reaction. So we're transferring a hydrogen and we're getting CO3 2 minus plus H3O plus. And so these guys are acid-base pairs, and so are these. And so HCO3 minus and CO3 2 minus are acid-base pairs. And H3O plus and H2O are acid-base pairs. And we're looking for the conjugate base of HCO3 minus, so that would be this guy. So then CO3 2 minus is our conjugate base. So the conjugate base of HCO3 minus can be determined upon removing an H plus, so that's true. But then they add one to give H2CO3, which is not true. So the conjugate base is CO3 2 minus, and so I'm just going to say this one's not correct. What is the conjugate acid of CH3 NH3 plus? So in this case, we're looking for a conjugate acid, so that means that this must be acting as our base. So we get hydrogen transfer this way. And it must be 2 positive plus OH minus. So then these two species are acid-base pairs, and so are these two. So then CH3 and H4 2 plus, CH3 and H3 plus are acid-base pairs. And H2O, OH minus are acid-base pairs. And in this case, so we're looking for the conjugate acid of CH3 and H3 plus. So it's going to be CH3 and H4 2 plus is going to be our conjugate acid. Okay. So now we need to determine the conjugate acid. You add one H plus. This is because they accept an H plus from the conjugate base from a base. The conjugate acid of NH3 plus would be CH3 and H3 plus. So that's the first part was correct, but the second part was not. So incorrect. The conjugate acid would be CH3 and H4 2 plus. Okay. Sodium hydroxide reacts with sulfuric acid in a neutralization reaction shown below. So they've given us our equation. We can understand it a bit further because H2SO4 is actually a diprotic acid. So it's going to give us HSO4. I should write it properly. So let's do it properly here. H2SO4 plus water is going to give us HSO4 minus plus H3O plus, and then HSO4 And I should stop making so many mistakes. So this is actually a strong acid, so it's going to go completely. And then HSO4 minus is going to be a weaker acid, giving us SO4 2 minus plus H3O plus. And sodium hydroxide is a strong base, giving us Na plus OH minus. So if we sum up these reactions here, we would cancel this, and we would need 2 times the OH minus to balance. There are 2 H3O pluses here, and so we would multiply this guy by 2. And so we would have H2SO4 plus 2 NaOH is going to give us SO4 2 minus plus 2 Na plus 2 H3O plus 2 OH minus, which these are going to balance into 4 waters. But there was also 2 waters on this side, so net 2 water. So I should add those in just to keep that. And is this not balanced, or was it not balanced in the question? 2, 4. Oh yeah, it's not balanced in the question. Okay, cool. And so these 2 waters, will drop that down to 2, and so it'll be H2SO4 plus 2 NaOH goes to, we can combine our sodium sulfate if it, just to match the question, although in reality it's going to be in solution likely as its ions, and plus 2 water. It should be 2, because if we look, right, there's 4 plus 2 oxygen, so that's 6. So we need 6 oxygens on this side, which is what we have. 2 plus 2 hydrogens is 4, so now we have 4 hydrogens, so that's the only way that this chemical equation will balance. But the number of waters don't really change the question or the solution, so that's the reason why it was left off in the question. Okay. So now to move on with the problem, so I just wanted to write out the equation because it's good for understanding where the 2 sodium hydroxides for sulfuric acid comes from. Okay, so what is the mass in grams of sodium hydroxide to completely react with 100 mils of a 0.5 molar sulfuric acid solution? So if our concentration of H2SO4 is 0.0500 molar, so that's moles per liter, and we have a volume of 100 mils, so now we can get our moles. So N is just our concentration times our volume, which is 0.05 moles per liter times 100 mils times 1 liter per 1,000 mils, just to for the unit conversion. So the mils will cancel, the liters will cancel, and we'll be left with moles, and that comes out to be 5.00 times 10 to the minus 3 moles. I'm just keeping significant digits in there. Yeah, because it's 100.0. And so that guy's 3 sigs, and that's 4. Now, it wants the mass in grams of sodium hydroxide, so we can relate our number of moles here from our balanced equation. So as we can see, per mole of H2SO4, we need 2 moles of NaOH. So that means that our number of moles of NaOH is twice our number of moles of H2SO4. And I should put H2SO4 here just to remember. So that means it's 2 times this value here, which is 10.0 times 10 to the minus 3 moles, again keeping the 3 significant digits. So our mass is our molar mass times our number of moles. So then our mass of NaOH, the question gives our molar mass as 40.0 grams per mole times 10.0. And so we're going to get 0.400 grams. Again, keeping things to 3 significant digits. And so then there's our mass of sodium hydroxide. So just relating it to the balance, so we get 0.01 moles, which is 10 times 10 to the minus 3. And so then putting this all through, we get 0.4 grams of NaOH, which I'm just using 0.400 because everything's given to, well, the only things that you need to worry about are the measured values for sulfuric acid, and the smallest significant digits there is 3, so 0.400. So I'd say the solution is correct. 0.400 with sig figs. So that's good. Okay. And we've got a 25 ml sample of 0.105 molar HCl titrated with NaOH. What is the concentration of our NaOH? Okay, so again, these are HCl's a strong acid. So we're going to get complete dissociation as the ions. And NaOH is also a strong, NaOH goes to NaOH, is also a strong base, so it goes completely into its ions. And so really what we've got here is a neutralization between H3O and OH minus to give water. And so our H3O plus and our OH minus concentration will always be in 1-to-1 ratios for a completely neutral solution. So if we've got 25 mils of a 0.105 molar HCl. So we can use this to calculate our moles. So remember, our concentration is our moles over volume. So our moles is our concentration times our volume. So 0.105 molar times 25 mils times 1 liter per 1,000 mils. So the mils will cancel, and I should have written this as moles per liter. So then the liters will cancel, leaving us with moles. Working this through, we get 2.62 0.2625 times 10 to the minus 3 moles. And so that's our moles of HCl. But from our dissociation constant of HCl, that is also equal to our moles of H3O plus. Oops. There we go. Clean stuff up a little bit. So then, but also from this balanced equation, our NaOH minus is equal to our NH3O plus. And then from this balanced equation, right, as everything's a 1-to-1 ratio, our moles of NaOH is equal to our moles of OH minus. And so if we put these all together, our moles of NaOH is equal to our moles of HCl, which is equal to this 2.625 times 10 to the minus 3 moles. Okay, so then what's the volume? Okay, so the volume is 315 mils. And it's looking for a concentration. So our concentration of NaOH is then our moles over our volume, which is 2.625 times 10 to the minus 3 moles over 315 mils. So we multiply by 1,000 mils per liter. Mils cancel, giving us a concentration of moles per liter, which is what we want. And this comes out to be 8.33 times 10 to the minus 3 moles per liter. Okay, checking with the solution here. So they combined everything together, that's fine. It shows that your NaOH and HCl are in a 1-to-1 ratio, so that's good. Your NaHCl can be computed from your concentrations as this, so 2.65. I don't know if that was my calculator or theirs. But since it's a 1-to-1 ratio, that must equal for the NaOH. And if we divide by 315 and multiply by 1,000, then we get this 8.33 times 10 to the minus 3, which is what they have there. So that looks good. And I'm going to end that here. So I'm going to say that's all my questions for today. If you enjoyed this, please subscribe to OneClass. If you want to leave questions, follow the links below the video. This has been Jeff Krause for OneClass, and I hope to see you